Hi everyone. This is Takashi Ishida, and I am a lecturer at the University of Tokyo and visiting scientist at Riken AIP. And we have been hosting TrustML Young Scientist Seminars, or TrustML YSS, which is a seminar series that features young scientists giving talks and discoveries in relation with trustworthy machine learning, led by Jing Feng on the very left here. And today is the 28th seminar, and I am excited to have Yaodong Yu to give us a talk about predicting out-of-distribution error with the projection norm. Yaodong Yu is a PhD student at UC Berkeley, advised by Professor Michael Jordan and Professor Yi Ma. He obtained his Bachelor of Science from the Department of Mathematics at Nanjing University and his Master of Science from the Department of Computer Science, University of Virginia. His research interests are in machine learning and optimization. Topics that he is actively working on include robust machine learning under distribution shift, federated learning, and understanding of overparameterized deep learning models. His goal is to make machine learning more reliable and robust. So Yaodong, we are very excited to learn about your research. And if you are ready, please begin.
Hi, everyone. It's my great honor to present our recent work on predicting out-of-distribution error with the projection norm at this very nice seminar. I'm Yaodong from UC Berkeley, and this is a joint work with Zitong Yang, Alex Wei, Yi Ma, and Jacob Stenhardt, all from UC Berkeley. And here is the link for the paper and the link for the GitHub, and all of us are from UC Berkeley. Here's the outline of my talk. So I'm happy to take any questions during my presentation. So feel free to interrupt me if you have any questions of a particular slide, or if you want to further clarification on certain notations or some details. So I'm happy to take questions during the talk. To start with, I will first introduce the motivation and the problem setup. So I will also try to pause at every subsection to leave for the questions. I will try to leave another 10 minutes at the end of the talk for some QA session. Yeah, here we are. For the motivation, suppose we have a deep neural network and we have a data set D, and the standard training process is we have a network, probably a pre-trained model. We fine-tune this model on this data set D, and then we got a model, which is the blue one, which is a trained model. So next question is how we evaluate the performance of this trained model. For example, suppose we consider a very standard classification problem, and then the standard or the standard way to evaluate the model is I take the model F hat, and then I take the data set D tutor. D tutor is the evaluation data set. And then we take the input of F hat and D tutor, and then we evaluate the test error of this, the error of F hat. So here is the formal definition of the data set D and the D tutor and the error function. So here we consider the average, the 0-1 loss of this to define this error function. And then the D is defined by n number of training data points, and xi, yi is sampled from the distribution P. And the D tutor contains m number of data points, and xj tutor and yj tutor are sampled from P tutor. And here, P and P tutor, for the standard case, P and P tutor are the same distribution. So here, so the common assumptions for evaluating the model performance basically has two assumptions. So here, first of all, we have the same distribution for the train and wall. Basically, during the test, the samples from the test are the same, sampled from the same distribution as the training distribution. So P and P tutor are the same. And second is that we have some available labels in the D tutor. So with the labels, which is YJ tutor, we can evaluate the model performance by plugging in this arrow function. So these are the two like standard assumptions we can make in the like standard setting for evaluating a model performance. So however, in practice, the P and P tilde could be different. For example, if we train our model on a clean image of a plant, and during the test, probably the image is corrupted by some noise or some snow or some rain, different conditions, and the distribution is shifted from the clean image to some other distributions. Another example is that suppose we are training a federated learning model, and we have some existing clients, and we are learning a model across the clients, but probably during the deployment time, probably there's a new client comes in, and we want to evaluate or we want to have a sense of how good the model is on this new client. The new client might be very different or kind of different from all the existing clients. A last example is a new environmental experiment. So the last row is contains samples from the WILDS dataset, which is RX1, is an image classification dataset. So on the left, the images are taken from one environment. And during the test, you probably want to use your model to predict for samples that are like conducted or extracted from another environment. So there is a difference between the training distributions and the test distributions. So here are some challenges during in the practice. Another like challenge, this is the first challenge in practice, which is P is not equal to P tilde. Another challenge is the labels are not available usually during the distribution shift during test time. So suppose we have the test labels during the test time, or we have a lot of labels for the new distribution. Then one simple solution might be we just refine tune or like retrain the model on this new distribution, then we can generalize too. But usually we do not have the labels for the new distribution. Instead, we probably only have the unlabeled data from this new distribution. So these are the two challenges in practice. Then we modify the problem a little bit. So we train our model on the training data set. We got our model F hat, and we want to evaluate we want to predict the model performance or evaluate our model F hat on a possibly shifted unlabeled data set, which is D tilde U. So we want to compute or predict the error of this F hat on this unlabeled shifted data set. So this is the problem we want to tackle in this work. So the question is, how can we evaluate the model performance under distribution shifts without having access to the labels? So this is the question we want to answer. So far, any questions or clarifications of the problem setup? Cool. So here in this talk, we want to propose a metric. This metric only takes into two components. One is the model, the trained model, which is F hat. Another one is the unlabeled data set that possibly sampled from a shifted distribution xj tilde j from 1 to m. And ideally, suppose we have access to a bunch of possibly shifted data sets. And then what we can do is we first, suppose we have four different kinds of data sets that this four evaluation data sets probably sample from different distributions that are shifted from the training distribution. So here, suppose for each data set, suppose we first compute the metric by taking this metric, taking the unlabeled data set in, and we compute the metric of this particular data set. Next, suppose we have access to some possibly shifted data, then we can use the actual labels to compute what's the actual error of this particular data set. So ideally, suppose we have such 4 data sets and we compute the metric of these 4 data sets, and then we compute the actual errors of these 4 data sets. And if such metric correlates pretty well with the test error, then we can kind of have a line or another kind of simple function that these points that are like kind of in a linear relationship or some kind of other simple relationship that correlates, metric correlates pretty well with the test error. In this case,
May I ask a question about
sure.
slide?
Sure.
So we have test labels for many distribution shifts, but we don't have test labels for the target distribution shift that we are interested in.
Yeah, exactly. So one kind of realistic or semi-realistic data set setup is that suppose in whiles we have different like distribution or data, different environments or domains. Suppose we have 5 or like more domains. We train our model on 2 of the domains, and then we train our model, which is f hat here. Then we can evaluate. We can treat these 3 domains as like some shifted domains, and then we can evaluate the metric and the error. Like what you said is totally correct. So we probably have access to some labeled shifted data sets. And during the deployment, there might be a new like distribution or new data set, possibly sampled from a new distribution, but we do not have the labels there. Then we want to like say, what's the model performance of this model on this new data set that compared to some existing data sets? Say, what's the position of this U in this plot? So that's yeah. Thanks for the clarification.
Thank you.
Thanks. Cool. Is this one? Okay. Next, one simple like or one possible approach to tackle this problem is that suppose we propose a metric that this metric correlates pretty well with the test error. And suppose just a new distribution comes in. And what we can do is we first compute the metric of this model on this new distribution or new data set. We have the metric value. And then through this metric value, suppose the relationship is kind of linear, then we fit a linear function here. Through this metric value, we can kind of estimate what's the actual test error is for this new distribution. So that's a very ideal case. Say we propose a metric that linearly correlates with the model, and then we have like a sense of how the model performs under some like new environments. So on the other hand, this relationship might not need to be like very linear. So suppose is some kind of ranking, like it's just a nonlinear relationship, but kind of predicted the rank of the shifts. So if there's a new like data set comes in, say the value is here, then we probably know, have a sense of what's the model performance of this like new environments. So that's a possible solution. So this is the approach we take to handle this kind of predicting model performance under distribution shift. So any questions so far, like for the setup? Cool. So next, we set up a few notations for like for some afterwards like experiments and models or theoretical understandings. So here we first rewrite the prediction model f hat as f parameterized by theta hat. You can think theta hat is the trained parameter of a neural network. And our training data set contains n number of training samples. And we have access to an unlabeled test sample or test data sets that are m number of data points. So our goal is we want to propose a metric or correlates well with the actual test error if we evaluate the model f hat on this d tilde. Like we in an oracle sense, we can evaluate the model performance of f hat on this labeled d tilde, but we want to like predict this test error or test accuracy. So in this setting, some standard machine learning evaluation methods do not work in this setting because there's some test time distribution shift. Suppose there's no shift, then we can partition our training data set into multiple parts, and then we use cross-validation to have a sense of how our model is generalizes in like on-same in distribution samples. But in this case, if there is distribution shift during the test time, we can now using the like standard rules or methods to evaluate the model performance. So next, I will present the method called projection norm. So before I start, any clarification questions on the problem setup or the motivations? Cool. Okay, so next I will present our method called projection norm. So here is a diagram for how can we compute projection norm with unlabeled data set and with access to the like training data. So suppose we first initialize our model with parameter theta 0 here, and then we train our model through using the training data, and we can train our model from theta 0 to theta hat. So this theta hat is the model we want to evaluate its performance. So in this work, we mainly consider the theta 0 is some like pre-trained model. So the setup is we have access to a pre-trained model, then we fine-tune the model on the training data, and then we got theta hat. So there are 3 steps to compute the projection norm in this case. Suppose we have the trained model theta hat, then we can use this theta hat to make predictions on the OOD data. So suppose we have access to the unlabeled data from the OOD distribution. Then what we can do is we can just make predictions on this unlabeled data set. We treat those predictions as pseudo-labeled because we can make the predictions just using the theta hat we just trained. Next, with the like pseudo labels, because previously we do not have labels for the OOD data. Now with theta hat predictions, we can have pseudo labels for the OOD data. Then from the same initialization, which is the pre-trained model theta 0, now we can use our favorite like supervised learning or ERM to initialize with theta 0 to train say cross entropy loss on this pseudo labeled OOD data, and then use SGD to train this to fine tune the model from theta 0 on the pseudo labeled data. Then we got theta tilde, and theta tilde denotes the parameters after the fine tuning on the pseudo labeled data set. So this is the step 2. And in step 3, we just perform a similar step, but not on the pseudo labeled OOD data. Instead, we further like fine tune or train a model on the training data. The procedure is we first sample or subsample the training data to be the same size as the pseudo labeled OOD data. Say we have 50K number of samples for the training, and we have 10K number of OOD data for the test. Then what we do is we first subsample the training data to 10K, and then from the same initialization, we use SGD to train or fine tune on this subsampled training data set. And then we have this theta hat ref, which is the ref means reference. And in practice, we found that if we replace this theta hat ref just with the theta hat, our method still works. So here is mainly for the purpose that for the consistency. Say we have the same initialization, we have the same number of training data points, and we are using the same optimization algorithm, which is the SGD, to like fine tune or train the model. And after getting theta hat ref and theta tilde, the projection norm is defined as just the L2 norm of the difference between theta hat ref and theta tilde. So this is the definition for the projection norm. So any questions on how to compute projection norm for the deep neural networks?
I have a question.
Cool.
So in this case, we have to use pre-trained model. So
yeah,
if we don't use pre-trained model, maybe the distribution of two in these two cases are so very different too much, and so so computed projection normal, well, it's too it's not stable, or I think so. But what do you think?
Yes, that's a very good question. So that's we also tried like the random initialized model, which there's one possible reason that first of all, we tried random initialized once, and it does not work very well for easy distribution shift. So overall, the plots look like some kind of predictions here. So here is the error. And for the harder distribution shift, it kind of predicts the train, but for easy shift, it does not give a very like very well predictions. And one possible reason is because of the network symmetry. So because suppose in a random initialized case, we have a W1 sigma, we have W2 sigma W1. Suppose this is the network we consider here. Then if we randomly shuffle the matrix of this W2, say just the neurons. So suppose we shuffle the neurons of the middle layer, and then we accordingly shuffle the neurons of the last layer, then the network is essentially the same. But if we compute the L2 norm between the parameter space between these two networks, the L2 norm is pretty large. So because there's some kind of symmetry here, then this kind of naively L2 norm between two models does not make that much sense in this case. However, if we have a pre-trained model, so suppose we initialize our model with a pre-trained weight, then overall, I would in the ideal case, in the pre-trained setting, the loss function is kind of convex with the theta 0. So this kind of pre-trained model with roughly break the weight symmetry such that this kind of L2 norm between the model weights does make a sense in this case. I'm not sure whether this answers your question.
Thank you. I got it.
Thank you. Cool. Thanks for the question. Yeah. Okay. Any further clarifications on the computation of projection norm? Cool. So here, another interpretation of this projection norm, to understand why this might be a good choice of, say, why it correlates well with the actual test error. Consider the following two extreme cases. Suppose the OOD data is just sampled from the same distribution of the training data. then you can think the training data and the OOD data are just like, the OOD data is just another copy of the training data, or they are roughly the same in terms of distribution level. Then in this case, suppose we initialize our model with a pre-trained weight. Then, and suppose our model generalized pretty well for the in-distribution data. Then you can just interpret the lower part, like it's kind of identical for this two paths. So because we from a pre-trained weight and we have like two very similar data sets, then it's very likely that we will like from the theta 0, if the like data sets are similar, then probably we just converge to like very similar solutions. In this case, projection norm is very small. So that's one extreme case that for the in-distribution data, if your OOD data are just a sample from the same distribution, then projection norm should be very small. In another very extreme case, suppose your model theta hat just performs very badly on a new distribution. Say the test accuracy are just a 10 or 0%. And in that case, what projection norm, the lower part is doing is that we've initialized with theta 0. We are training on a like very label corrupted OOD data. Then in this case, it's very likely we will converge, or the theta will converge to a very different solution compared to theta hat ref. In that case, the projection norm will be very large, and the test error will also be quite large in that case. So that's two interpretations of projection norm, or two extreme case to understand why projection norm is kind of makes sense to capture the model performance. So later I will try to further understand the performance or what projection norm is doing in the over-parameterized linear regression model. And roughly speaking, the both step 1 and step 2 combined together is kind of a nonlinear projection that project the model weights onto the OOD data manifold. So I will try to explain this further in the linear regression setting. So you can treat the first two steps are like nonlinear projections. So that's the method, like how to compute projection norm. And any further questions, clarifications on the computing projection norm part?
So may I ask two questions about?
Sure.
About so you explained the extreme cases. So when the two thetas are very similar, and when we use like in distribution data, so can we also use this to predict test error for in distribution data?
Yes. So for this, so suppose if we know the in distribution data, or if we know the data are sampled from the same distribution, then one simple strategy to predict the model performance is we first partition the training data into train and law. And then we train a model on part of the training data, and then we evaluate the model on the validation data. Then that model, like that test accuracy should be like kind of generalized to new like in distribution data. So in this case, if we know the distribution is sampled from in D, then it's very easy to compute the model performance. I will try to show like we also include the in distributions performance in the like later experimental results. I will try to reflect that in the scatter plot. Yeah. Overall, like we considered in distribution in the evaluations. Yeah.
I see. Thank you. My other question is the other extreme case. So when we have a very different out of distribution data set,
yes.
And if the projection norm becomes a lot bigger, did you see some cases where the predicted error is above 1? Or because we have a linear regression, but we know that we have domain knowledge that the error should be between 0 and 1?
Yes, that's a good question. So that's about like some, suppose we have different pairs, how should we calibrate the function we want to like, how should we make the predictions after we have seen like different like points on this metric versus the test error? I will try to reflect, like emphasize or discuss this in later like scatter plots. Yeah.
Oh, okay.
That's a good question. Yeah, that's a indeed for some cases, for some baseline approaches, existing approaches for the adversarial distribute, like if we put adversarial perturbations to the as the distribution shift, we indeed give some like unreasonable predictions under that challenging case. I will show that like in later parts. Yeah, that's a very good question. Yeah.
Okay, thank you very much.
Cool. Then let's see some experiments. Try to convince you like this is kind of useful. And then after I convince you this is useful, I will try to provide some insights from an overparameterized linear model, say what projection norm is doing in the linear case. So now here is the scatter plot, the mainline experiments we considered in the paper. So the data set is CFR 100C, which corresponds to the corrupted version of CFR 100. It contains 16 corruptions, and each corruption has 5 different severity levels, say whether the corruption is kind of large or small. So in overall, there's 80 corruptions here. And we also put the in distribution like data set in this scatter plot, which is hidden in this place. So then let me further parse the scatter plot a little bit. So here the x-axis is the projection norm. So given one, so the y-axis is the actual test error. And every point in the scatter plot corresponds to one type of shift. Say there's one corrupt, for example, for this point, it corresponds to one corruption with one severity level. And then we can compute its projection norm with the unlabeled data. And we can also compute its actual test error. Suppose in Oracle way, we can compute its test error for this one type of shift. Then we put all the pairs of projection norm and test error pairs on this scatter plot. And here is the like scatter plot for our method on this particular data set. And the model we considered in this case is the ResNet 50 pre-trained on ImageNet as our zeta 0. So this is the scatter plot for like overall experiments we did to evaluate how good our method is for predicting like the test accuracy. So suppose there's a new type of new data set that the new data set has a projection norm at this value. And what we can do is we can like kind of estimate its actual test error like by doing this. So this is one way to like kind of predict the model performance. And in the extreme case, as Takashi mentioned earlier, it is possible that the projection norm could be very large and the test error could be like above 100. That's also possible. So we did not see that case in these experiments, but it's for practice, it is possible that the projection norm is, if we fit a linear curve or if we fit a linear line of the scatter plot, it's possible that the projection norm will lead to a larger than 100 test error in that case. Probably we need some calibration in that case. But for the data sets we considered in this work, we did not see that case happen. This is the mainline experiments. Any questions on the like how to plot this or how to evaluate the method? Cool. So We also consider some baseline or benchmark method for comparison. So here we consider the confidence score, which corresponds to, we take the softmax of the model output, and then we take the max of the softmax vector, and then we average this value across the test data set, and this corresponds to the confidence score, which is also named the MSP. And the ATC is kind of another variant of such method. It tries to learn a threshold and then make predictions by using the threshold. And the agreement score is another type of method that kind of we first independently train 2 or more models on the training data set. During the test, we can use these multiple models to make predictions on one single test sample. And we can check whether different models agree with each other on this particular sample. We can compute an agreement score on one sample, and then we average such scores across all the data points in the test data set. And that corresponds to the agreement score. And rotation prediction corresponds to, it modifies the network architecture a little bit. Instead of just doing the classification prediction, it also makes predictions on the rotations of the image. Say, suppose we have an image during the training, we can rotate it 90 degrees, and the rotation label corresponds to 1, and the 0 degree corresponds to 0. And then for one image, you have you can augment another 3 images here, and then you can make predictions during the training. And during the test for one sample it comes in, because such rotation labels is kind of in an unsupervised way or a self-supervised way. You can estimate the model performance of the rotation prediction. And in this work, they found that the rotation prediction performance kind of correlates well with the actual test performance. So these are the main existing methods we considered in this work for comparison. So here are we did some realizations of different methods, 2 methods compared to ours, have a sense of how different models or how different methods perform on this data set. So here we found that the ATC and the confidence score performs pretty well on easy shifts. This corresponds to the area that the test error is not that large. Say if the test error is below 50 or 40, this relationship is very linear. On the other hand, if the test error is large or for the harder shifts, so the confidence score and ATC do not perform that well. For example, for the same confidence score, the actual test error could vary up to 30 or around 30%. This is some kind of undesired property we want to avoid. So overall, we found that a projection norm get better performance for harder shifts and do okay on easy shifts. Overall, our method is kind of linear compared to, or is more linear compared to existing approaches. So here is the evaluation of projection norm under 3 data sets with different architectures. We considered R-square, which is perform a linear regression on the scatter plot and see how the metric and the actual test error correlates with each other. And that only captured the linear relationship. We also consider the rank correlation, which could capture the nonlinear relationship. And we use these 2 metrics for evaluation. And we found that our approach performs better than existing approaches across different scenarios. And overall, we get better performance on these different scenarios. So here is another more fine-grained analysis on projection norm. We found that because all the existing approaches, they are kind of doing some computation, or the metrics are computed by the model output. say I have input, I go through the network, I got the last linear or second last layer output, and for last layer output, we compute some metrics based on those outputs. However, those are like only based on information from the model outputs. However, projection norm, we are computing some information for the model like parameter space instead of model output space. In this case, we found that the errors made by previous approaches, say confidence score versus ATC, so here they are kind of linear, say they are making similar mistakes, but projection norm are kind of orthogonal to the previous approaches, which kind of provide an orthogonal signal to the existing approaches. So here are some ablations for the projection norm, which is we investigate the role of pseudo labels in this case in projection norm. So suppose we just use the oracle like labels in the projection norm. Instead of using pseudo labels, we use the actual true labels for training the C-CUDA, and we found that with the actual true labels, it actually performs worse compared to the pseudo labels. See, the pseudo label is kind of an essential part for making projection norm work better. We also try to vary the number of, because there are some other parameters in the projection norm, because we need to use the SGD to fine tune the model. And there's the training iterations and number of training data, number of training samples in that case. And we found that projection norm kind of stable across all the scenarios. So these are the experiments part. So any questions, clarifications for the experiments?
The scatter plots look very nice. And I was wondering if you were surprised by your results, or were you already kind of expecting this kind of, or did you have a strong intuition before you worked on these experiments?
Yeah, thanks for the question. So actually, like how we discovered this method is we first propose a projection norm in the over-parameterized linear model case. And then we build a connection between the linear model and deep neural networks. And then we like propose this deep neural network version of projection norm. Actually, in the over-parameterized linear model case, this kind of trend is less surprising than the deep network case. So yes, we are like we were quite surprised why this projection norm works pretty well in this case, because we did very naive things or very simple things. We just compute the basic like L2 difference, and we did not like pick which layer to compute. We just concatenate all the parameters and compute the difference. So yes, overall we were quite surprised actually. Yeah.
I see. Thank you very much.
Yeah, thanks for the question. Cool. Then let's try to get a better sense of what projection norm is doing in the over-parameterized linear model case. So first of all, we first consider a simplified over-parameterized linear regression model. So here we made another few simple notations here. So previously we have x, I, y, I sampled from P. Here we have a number of data points. We denote this data matrix as X, and we denote the labels or the labels as Y. Y is a number of n-dimensional vector. And then the OOD test data we denoted by X-CUDA and Y-CUDA. And we have m number of OOD test samples from like during the test. Next, the first assumption we make is the covariance shift assumption. Specifically, we first assume D is much larger than N, which is the over-parameterized regime that kind of capture or aligns better with the like deep neural network case. So you have more parameters than the number of training data points. And then we assume that there exists a zeta star such that zeta star could correctly label both the in-distribution data and the out-of-distribution data. So this is the first assumption, say, kind of in the noiseless linear regression case, say there exists a zeta star that make the equation like hold. And next we define what is the zeta hat or f hat in this linear regression setting. So because the problem is over-parameterized linear regression, it's natural to consider the mean norm solution, which is we want to found a zeta such that x multiplied with zeta equals to y, and we want to found the mean norm or the solution with the minimum norm. And we can write down the closed form solution of this mean norm solution. And then after plugging in, because we have this assumption that y equals to x multiplied with zeta star, then we can plug in this y with x zeta star. Then the solution of zeta hat is essentially that projecting this zeta star to the row space of the training data. So suppose we just compute the span of our training data, because here the problem is linear. We just project, we have access to the zeta star only on the training span of the training data, or the span of the training data. So here P is the projection matrix of the training data X. And next we define like what is the projection norm in this linear case. In this case, the projection norm linear is defined as follows. So we have this zeta hat, which is the model we train on training data. And the zeta tuta is computed as follows. We first projecting the zeta hat onto the row space of OOD data. So P tuta is the projection matrix for the OOD data. And then we compute the difference between zeta hat and the zeta tuta. Sorry, this is the typo. So this is defined as zeta tuta. And this is the definition for the projection norm linear. And interestingly, what we found is that this zeta tuta can be interpreted as the mean norm solution to the following problem. So the problem is, the interesting part is we have the access to the x tuta, which is the OOD data. And we have access, and then we use our trained model, which is zeta hat. After multiplying with zeta tuta with x tuta with zeta hat, this kind of can be treated as the pseudo label. So we first use zeta hat to make predictions on the pseudo label. Then we treat this as the pseudo labels of the OOD data, and then we solve a mean norm solution for this problem. And suppose if we rewrite our previous function f as an inner product between the data and the parameter, then this is exactly the like pseudo label we mentioned earlier. Say we use zeta hat to make pseudo labels here, and then we solve this this quadratic loss problem, and we solve the mean norm solution. So let's just call back what projection norm in the deep network case. So recall that we have a zeta hat, then we use zeta hat to pseudo label the OOD data, which corresponds to this part. And then from the same initialization zeta 0, in this case, we can treat this as the 0, like from the 0 initialization. And then we solve a mean norm solution using the closed form. The interesting part is, suppose if, because in the deep network case, we are using SGD to solve or to get the solution of zeta tuta and zeta hat rep. And for the quadratic, for the regression problem, instead of using the closed form solution, if we use SGD to solve this problem, say we initialize zeta 0 with 0, and then we use SGD to solve this problem, then by the implicit bias of SGD, the theta will actually converge to the mean norm solution of the problem. Therefore, like in this linear case, we kind of do a one-to-one mapping between the relationship. So we do pseudo labels, then we do like SGD fine tuning, and this is the relationship between what projection norm linear and the projection norm in the deep network case. So basically, what projection norm linear is doing is that we have a theta hat. We want to compute like what's the norm of after projecting theta hat to the orthogonal space of the OOD data. So suppose the OOD data form a span. We want to project the theta hat to the orthogonal of the OOD data span. So that's the intuition, or that's the interpretation of what projection norm linear is doing in the linear case. So any questions on the projection norm linear in the overparameterized model? Cool. So I will skip the theoretical parts. So basically, we made a few assumptions for the overparameterized linear model, and we can prove a proposition that the test error could be upper bounded by projection norm linear with a constant here, and lambda k plus 1 is the k plus 1 largest eigenvalue of the test covariance matrix of the OOD data. So due to the time, I will skip this part. If you have, if we're interested in this part, we can discuss in the QA, or you can refer to our paper. So another interesting observation we made here is that we actually try to examine whether the linear model makes sense for some semi-real data sets. So here we try to extracting the empirical neurotangent kernel representations, say from a pre-trained model. And then for each image or each input, we can obtain the neurotangent kernel representations and form this as a like high dimensional vector. Here D is much larger than the number of training data points because the ResNet 18 has more parameters than the number of training data points for CFR10. And then after extracting this high dimensional vector, we actually form this, we actually compute the projection norm linear by solving an overparameterized linear model. Interestingly, in this case, here x-axis is we compute the projection norm linear on the neurotangent kernel, empirical neurotangent kernel representations. And on the y-axis is the actual like fine-tuned network f hat evaluated on the labeled shifted data. So in this case, we found that the projection norm linear computed on the empirical NTK actually roughly predict the trend like of the actual like model performance under distribution shift. And the actual model is like fine-tuned from a neural network by actual SGD. So kind of a little bit justify like why the linear model is kind of a good choice in the first place empirically. And here is another synthetic example. We constructed that the projection norm can capture the signal or capture the orthogonal direction of the training data. So here, the things are like the training data are sampled from this covariance matrix. A Gaussian, the covariance matrix has an identity for the first D1 components. And the test distribution or test data are sampled from a Gaussian, but has a noise part. So suppose we just change the noise sigma to change the level of shifts. And in this case, for the confidence score or the like softmax output, the confidence score will not change at all because the model learned or only captured or only learned for the first D1 components. And it does not learn anything beyond the first D1 like elements. However, the projection norm can capture the remaining directions. and provide a useful signal. Say the green curve corresponds to the projection norm linear, and the blue curve corresponds to the actual test error. In this case, the projection norm linear can actually like provide a kind of a useful trend for predicting the test accuracy. So this again, this is like synthetic experiments, but it kind of gave us a sense of why like projection norm can provide an orthogonal signal to the existing methods. So next, I will briefly introduce a few challenging cases for projection norm. Before I jump into the last part, any further questions on the linear model part? Cool. So the stress test we consider in this paper is we consider like the extreme case of shift, which is adversarial shift. So here we constructed our infinity white box PGD attacks on the validation data. And we control the level of shift by tuning or changing the parameter of epsilon, which is the how large the perturbation is or could be. And in this case, the stars correspond to the like different levels of epsilon. We found that, for example, if we make larger epsilon for a confidence score, the confidence will be like close to 1, but the test error is actually like 100 like 100, like zero, like zero test accuracy. But if we fit a line here, then the predicted accuracy could be like smaller than 0. So it's a perfect classification. But however, like it does not like give useful predictions on this adversarial shift. Projection norm kind of gave useful predictions. However, it does not align pretty well with the natural distribution shift. So it's still a challenging case for the projection norm to predict under adversarial distribution shift. However, it's slightly better than existing approaches. Say they are giving the opposite like prediction trend. Another limitation of projection norm is that our method only holds for one particular type of data set. So suppose we consider it's not like calibrated across different data sets. Say if we plot the CVAR 10 and CVAR 100 into a same plot, it's kind of not it does not calibrate it that well. So we probably need some calibrations for projection norm to make it on the line. Another limitation of projection norm is we do not do that well under easy distribution shift. So here is the scenario that we first take out the CVAR 100 validation dataset, then we partition the dataset by classes into easy and hard shifts. So the easy classes versus the hard classes into 5 groups. We found that projection norm kind of predict the trend, but not as good as the like existing approaches. So overall, the projection norm can give better like test error predictions on harder shifts, and it makes use the full data set instead of just using one single like test sample. So however, it has several limitations, and it also has we are still working on like some variants or improvements to further improve the projection norm performance. And that's all for the moon context. So I want to share. So any questions for any parts of the presentation? Yeah.
Thank you, Yaodong, for the great talk. If anyone has any questions, please. Or you can also use the chat box.
Yeah, feel free to ask any questions if you have any.
So I think we need a lot of out of distribution data sets in order to do the linear regression. So I was wondering how difficult that would be in practice. So if we have image data sets, will this be quite easy because we can automatically make the out of distribution data sets?
Yes. Yes, that's a very good question. So I think, first of all, I think one thing probably projection norm could be useful is because we have some existing approaches for predicting the model performance. Say some of those are calibrated under like distribution shift. For example, if we have the confidence score, I think one useful part of projection norm is we can, for one type of distribution shift, we can compute both the confidence score and the projection norm for unseen like tested distribution. And we can also compute these two quantities for the in distribution. And if both quantities are quite close to the in distribution data or in distribution validation data, then we're probably kind of confident that probably the model will just perform similar as the previous in distribution data. Regarding secondly, like I think in some cases it's kind of there are some existing data sets. For example, WILES, it contains like multiple domains for they have multiple domains for the OOD evaluation. So probably in practice you have access to several OOD data sets that are not used during the training, but you have some labels for those OOD data sets. And then in that case, you can create such scatter plot to make it in a linear trend. And another simple way to create such different kind of shifts is the subpopulation shift, which is suppose we have multiple classes or we have different kind of clusters of the data set. Then we can divide the whole validation data set into different levels of difficulty. So we divide the validation data into 2 parts or 10 parts, and every part just the difficulty is different from the others. Then without creating new OOD data, we just create some kind of subpopulation shifted version of the in distribution data. This could also give us kind of a plot for like evaluation. Like suppose you give me a new tested distribution, I can like kind of know where it locates. Like it's easier or it's harder than the hardest data set for our in distribution. Yeah, that's probably one possible like approach to tackle the problem. But overall, yes, I think we still need like collect many kind of different domains of OOD data to create such a scatter plot. Yeah.
I see. Okay, thank you very much.
Thanks for the next question. Yeah.
If anyone else has any questions, please. Okay, if not, let's end the seminar. Thank you again, Yaodong, for the great talk. That was very interesting. Yes.
Thank you so much for your invitation. It's my great honor to speak here. Yeah. And thank you all for your questions and like feedbacks. Yeah.
Thank you.